Hey everyone, our presentation today is going to discuss our plant design for the conversion of a natural gas feed to a methanol product. Before we begin, we'd like to introduce ourselves first. We're Team 7 up till the break of dawn. All 4 of us are seniors majoring in chemical engineering here at Penn State. My name is Dino Cuturic, and my colleagues are Niko Mavreles, Nate Sauers, and Selina Roman-White. So with that, let's get started. Our objective for this project was to design a methanol plant in the city of Philadelphia here in Pennsylvania. This pilot plant was to be built directly on the river. This was beneficial because we were able to use river water for use in our plant process. There were several other benefits as well, including the fact that there were local shipyards and rail lines that we could make use of for transportation. This was a benefit along with the fact that there are plenty of local engineers available in Philly for our pilot plant construction. So now our plant was purchasing a sour natural gas feed stream at 36 mm SCFD. This is million metric standard cubic feet per day. Since we're purchasing this stream, there were several set in stone specifications that we had to deal with and work around in our plant. These included the temperature and pressure for the inlet stream, which were coming in at a temperature of 80 degrees Fahrenheit and a pressure of 400 psia. Along with this, we also had a composition for our stream that was set in stone. And this composition can be seen here on this pie chart. This is by mole percent. The majority of our inlet feed is CH4, or methane, at a 90.11 molar percent. The rest of it is broken down in this other pie chart, which shows several other components or impurities that were present in our inlet feed that had to be dealt with in our plant process, which I will discuss. For example, some of these included hydrogen sulfide right here, which had to be dealt with, for example, by constructing an entire desulfurization unit to remove it from our stream, because it's known to be harmful to the environment and we couldn't allow it to be present in our stream. Along with this, there were other components as well, such as mercury and nitrogen, which also needed to be removed from our plant process, and those were taken out. So moving on, we also had a series of hard specs that we needed to meet for this plant design. These included the fact that we needed to convert a minimum of 90 mole percent of our methane in the inlet feed to our methanol product. This hard spec was combined with the fact that we needed to have a target purity of 99.85% for our methanol product, and these specs needed to be met for our final target. These were done using a number of different reactions and methods. These include the use of a steam reformer in our plant, as well as the Fischer-Tropsch process, and this will be discussed in further detail by my colleague Niko in just a moment. But with that, I'd just like to say that today, my partners, we're going to focus on the design, economics, and our recommendation for this plant. And with that, I'd like to pass it off to Niko.
Thank you, Dina, for giving us an overview of the project. I'm now going to be talking briefly about our process and the basic components of it. So we can break our process down into 3 main sections to make it easier to understand. First off, we have the pre-treatment stage. This is where the components of the feed stream that we don't want in the reactors are removed. Second off is the reaction stage, where our main reactions of the syngas production and methanol production are located. And lastly, it's a purification stage, where our purity specification of 99.85% is met. First off, the pre-treatment stage. This removes sulfur, mercury, and heavy wastes such as butane and pentane from the process stream. First off, the feed stream enters a desulfurization unit. This unit is pretty much an absorption tower using MEA as the absorbent. This removes both sulfur and mercury from the process stream. The remainder of the stream then travels to another separator, a vapor liquid separator, that removes butane and pentane from the stream. The remainder of the stream from the desulfurization unit, which contains primarily MEA, sulfur, and mercury, then heads down to a waste stream where the MEA is purified and recycled back into the desulfurization unit. The remainder of the two streams, containing sulfur, mercury, and the heavier hydrocarbons, are then sent to a waste stream, while the process stream travels to the reactors. So the reaction stage has two different reactors, the syngas reactor and the methanol reactor. The first reactor takes water, the process stream, carbon dioxide, fuel, and air. The fuel and air are used to heat the stream up because we're holding the reactor at 1,000 degrees Fahrenheit, and we really need a fired heater in order to heat it up to that temperature. There are several different reactions that take place in this reactor. Primarily we have methane, ethane, and propane reacting with water to form different stoichiometric ratios of carbon monoxide and hydrogen. These are the main parts of this reactor, and this is what will travel to the methanol reactor. But we also have a water-gas shift equation, which takes carbon monoxide and water to form carbon dioxide and hydrogen. We decided in our process that we didn't want to have too much of this reaction. While it can be used, we didn't want it in our case. And to prevent this, we pumped in carbon dioxide. What this will do is shift the equilibrium of the water-gas shift equation towards the reactants. And so we don't really see this reaction too much, if at all, in our syngas reactor. The products of this reactor, which is primarily CO and hydrogen, are then sent to the methanol reactor. The methanol reactor also takes air and fuel for the same reason as the syngas reactor. However, in this case, the reactor is held at 490 degrees Fahrenheit. There are 5 primary reactions in this methanol reactor. The most important one is the actual methanol production from carbon monoxide and hydrogen, and that makes up most of our methanol production. Secondly, we have carbon dioxide and hydrogen forming methanol and water. We see this to some extent because carbon dioxide and hydrogen are still present, left over from the first reactor, and so this contributes partially to our yield. We also see ammonia being produced from hydrogen and nitrogen. However, this is essentially zero, and the amount that's produced can just be removed in the purification stage. Lastly, we have 2 other products from carbon monoxide and hydrogen, methyl formate and ethanol. Fortunately for us, the selectivity of methanol is about 99.6%, leaving the remaining 0.4% for the other 2 products. Because of this, those 2 products can just be removed in the purification stage with little issue. So the purification stage removes impurities to produce the purity specification. So first off, we have the process stream entering the methanol purification unit. This starts out with a vapor liquid separator, which removes nitrogen and carbon dioxide in the vapor stream, while sending a stream rich in methanol and water in the liquid stream. This stream then heads to a series of 2 large distillation columns. The first one brings methanol to a purity of about 99.7%, while the second one allows it to meet the 99.85% purity specification. So the distillate of this column then heads through stream 12 to the tankers for storage and transportation. We also have the distillation waste from the first distillation column stream. And from the second distillation column stream, we have a stream very, very rich in water, with also some other wastes in it. And this set is sent over to the water purification unit, which consists of a large distillation column where water is purified. The impurities from this are sent to just a waste stream, while the remaining purified water is mixed with purified water from the river feed, and then this mixed stream is then sent to the syngas reactor, where it's used to power the syngas reactions. So that's a basic overview of the primary components of our process. Now I'll pass it over to Nate, who will give us some detail about the economic factors that went into our project.
Well, thank you, Niko, for showing us the plant overview. I am now going to go into a bit about the economics of the plant. So, our IBL capital estimate, which is the equipment inside the plant, totaled to about $34.4 million. The biggest contributors to that were these 4 pieces of equipment here. Now, each of them have a special reason for why they contributed to so much to the IBL. So our fired heaters, the 2 of them came in at about $5.5 million. This was because the material of construction needs to be strong because of the temperature that the fired heaters reach. They were used to heat our process streams to 900 and 490 degrees Fahrenheit, so the material of construction needed to be strong, especially around the firebox. Because of the different sections in the fired heater, we only use the radiant section, but because of the other sections for the exhaust gas, they still need to be large and have a large area. So that is why the 2 of them totaled to about $5.5 million. Next, we have the compressors, total to about $6 million. We have 2 of them. One compresses the process stream to 7 megapascals. This pressure was chosen because this is the ideal conditions for the methanol reactor in order to produce methanol, and it's unfavorable for the other reactions occurring in that reactor. The other compressor was used to compress the gas stream entering the flare, and because of the size of the compressors compressing the gas, it contributes to a large cost. Next, we have expanders, $6.3 million. There's 5 of them in series. The reason is the flow rate coming out of the methanol reactor is so large that one expander cannot handle it. So we decided to put 5 in series to be the cheapest in order to expand from the 7 megapascals to the 1 atmosphere conditions. Then we have heat exchangers totaling $4.1 million. We have 9 of them, and the reason is that we decided, because of the fact originally we had 4 compressors compressing our stream to 7 megapascals, and we found that that was very inefficient and very expensive. So we decided to cool the stream exiting the syngas reactor from 1000 degrees to 50 degrees. So that constituted putting 5 heat exchangers in series in order to cool it using different pressures of steam in order to get the temperatures down to what we needed to separate the vapor and the liquid. Also, entering the syngas reactor, we had 3 heat exchangers in series in order to decrease the duty that the fired heater needed to perform. Doing this ensured that we actually had smaller fired heaters, and that saved cost there. Our other heat exchanger is in the main area of our plant, and that is to cool down our process stream so that it can be pumped to the proper pressure for wastewater filtration and removal. So if we look at our yearly ongoing costs, most of it is constituted by utilities. This is the purchase of our natural gas fuel for our fired heater. This is the purchase of steam for the heat exchangers, and this is the power needed to power our compressors. Next, we have raw materials, and that is the purchase of the feeds for the different reactions, such as the feed gas stream itself and for the carbon dioxide used in the 2 reactors. Our fixed costs at 15%, that is just our labor force and everything like that. And our 2% SG&A are for sales and administrative fees that we would need to pay. Now looking at our OBL, which is storage outside of our plant. Our largest is the natural gas utility storage for the fuel for the fire and heaters. This is because of the flow rates. In order to use enough fuel to heat our streams up to the desired temperatures, we need a lot of storage for the natural gas utilities. Our next highest is the methanol storage, and that is used right before the methanol goes put into the tankers. We need to store it in the plant. So that is our next largest. Then we have our site development, just building and everything with the plant, and our environmental, which is wastewater storage and removal. And then looking at this graph, this shows our cash flow from our start year of operation until our plant shut down. We become cash positive in 7 years, and we have a total production cash flow of $480 million. Now you notice here we have a dip in the negative. This from 2017 to 2019 are our 3 building years where we split up our capital costs over those 3 years while we're building the plant. 2020 right here is our first year of operation where we're only operating at about 25%. And then 2021 we ramp up operation to 70%. 2022 right here is our first year at full operating capacity. And then as you can see, our cash flow goes up until we hit the end of our plant life because we were only operating for 15 years and we have the plant shut down. I'm now going to hand the presentation over to Selina Roman-White, who will continue to discuss economics and make our plant recommendations.
Thank you, Nate. I'm going to continue with the economic analysis. So you'll see that we calculated our cumulative present net worth, and we become present net worth positive in the year 2025. The reason that the plant does start out negative here is because operation doesn't begin until year 4, and we don't reach 100% capacity until year 6. But in the year 2025, we do become positive and continue to increase going forward. You'll notice the slowdown at the end. That's because we assumed that at the end of the life cycle in the last year, we would be at 0% capacity. The plant will end with a present net worth, a cumulative present net worth of $128 million, a sizable amount which is promising for the future of the plant. We also calculated the rate of return under the base assumptions. We found that we would have a rate of return of 20.8%, which is well above our target of 15%. Looking at the after-tax revenue, you'll see that we meet our required netback in 2022 and continue to increase in revenue going forward. This, of course, takes into account income tax, which we assumed a rate of 35%, and we also accounted for inflation, which would deal with an increase in operating costs. So even after inflation and taxes, we continue to increase in revenue and be profitable in the future. We recommend that under the current market, we should build this methanol plant because based on our technical and economic analysis, this plant is sound and would be profitable. But to even strengthen this recommendation, we did some sensitivity analysis on the economics. First, we looked at the raw material costs. We found that the raw material costs could increase to as much as 3.5 cents per pound and still meet our rate of return, a target rate of return of 15%. We also looked at the utility costs and found that our utility costs could increase to as much as 5 cents per pound of product and still meet the rate of return of 15%, which is a great margin to have. We looked at our capital costs. We found that we could increase an additional $50 million off of our base capital cost estimate and still meet the target rate of return of 15%. And lastly, we looked at the time to enter the market. So originally we assumed that it will take 3 years to construct the plant and enter the market. That could take as much as 6 years, increasing an additional 3 years to enter the market and still meet our target rate of return of 15%, which is a great margin to have and promising for the future of this plant. Of course, before we would construct this plant, there are a few factors that would need to be considered more in depth. First of all, we would need to take a closer look at the environmental aspects. Make sure that the plant would meet all EPA recommendations, especially looking at items such as emissions and waste streams. We also should take a closer look at process controls and safety controls, making sure that the plant would be safely operated and under control. Lastly, while all equipment was sized, we need to develop a site plan where all the equipment would be placed on the site in an efficient manner. But even though these things need to be further considered, we do recommend that this plant should be built because in the current market, it will be profitable and be an asset to this company. Thank you.